Like, ahead of time, there will be no questions on like the first half of the course, except maybe like the borderline topics. So the topics which are right before the midterm exam. So, anyways, the final exam is mostly written. I will probably reshuffle the questions, maybe replace some questions with the other ones. I'll like try to evaluate them from as if I were a student. So it's mostly written, so I can basically tell you what the course is. So final exam, in case you haven't noted anywhere, so it's early in the morning on Saturday.
It's not 9 p.m.?
Yeah, that's 9 p.m. So or
9 a.m.
Sorry, 9 a.m. 09.
I'm just trying to trick you.
I just use the 24-hour clock normally. So anyways, it's on the 20th of December, right before Christmas.
That's cool.
So the location, building. I'm not sure if these rooms are like the same room or if it's like two different rooms. Okay, so we'll see how that works. The exam will be 2 hours long, and probably even 2 hours will be too much time. So, my experience, most of the people will write it like in 1 hour 10 minutes. So, generally, I do not limit the time in my exams, so it's not like you will not have enough time to write your answers. Okay.
Provided that, say we do need extra time, would that be okay?
So 2 hours is basically the allocated time.
Okay.
So, final exam format, 12 to 13 questions, like plus minus 1. The minimum is going to be 12, maybe the maximum is 14.
So no programming questions at all?
No programming questions because, like, come on, like, what am I going to test you on, like, Swing? I'm not teaching Swing here, I'm not teaching Java here, so if you want to know Java or, like, how to be a great programmer, this is not the best course for that. It's not about programming per se. So, so that's why I decided to test you on something that actually makes sense for this particular course. No, there will be no multiple choice questions, so most of the questions will be like either short answer, like 1 or 2 sentences, or longer answer, which is like 5 to 6 sentences maybe. I think that like each question is basically a question. There will be no sub-questions as far as I'm concerned. So yeah, these are just individual questions. Some of them will require more time for you to answer, some of them will be extremely short. The topics, as you can see, is pretty much all of the topics which were covered after the midterm exam. So I think I didn't leave out anything. So the stuff which is currently not in the final exam, but I'm considering adding it. So things about latency, jitter, dropouts. Things that were covered right before the the midterm exam, something on display technologies, on color and text. Was there a question?
Yeah. This is up on the website?
Yeah, this set of slides has just been posted to my website. So everything you see on the board is also on the website. So, anything that's missing here? So yeah, let's just go over quickly. Go over all of the questions really quickly. So the things that I considered worth remembering, or like the things that kind of indicate what was taught during that class, during those classes. So it's a very condensed review. It doesn't substitute. This is not a substitute for like reviewing all of your notes. Reviewing all of your slides, maybe glancing at the book. So this is very condensed. So basically all of the slides have been compressed into like 25 slides. So MongoDB controller. Know what model, what view does, and what the controller does. Know what they are for, what they are responsible for, how you implement them, why you use them. So what objective you're trying to achieve by using this separation of the MongoDB controller. So basically know the basics. MongoDB controller and Swing. So how MongoDB controller is implemented in Java Swing. It's slightly different. There is a thing called UI delegate. There is several models that you can use, so different widgets can have different models. You can implement your own. So the model basically is an interface. You can implement your own models instead of using the default ones. Look at the examples. Yeah.
You were saying how to implement it, like.
So if the question is actually like in what classes will you put the following implementation, like questions like that. You will not have to write your code, but you will have to know like how this code is actually composed, like where to find things. So please look at the examples, try to understand how it's basically implemented. So swing models, at least have some rough idea that different models exist and what models you might be using for simple widgets such as buttons or tables. So look at these names, try to be able to try to remember what other models can do and like what they store and how you can implement the models differently and why you might want to implement the models differently, not just use the default implementation. Let's say you have a table. Why would you not want to use the default table model and you want to implement your own? Like, try to think about like, why the non-default models might be useful. Component UI class, like how it's composed of classes, like what is children classes and the subclasses and so on. Now, other stuff, human factors, essentially, controls and displays. What the controls are, what the displays are. So, what the humans, like the input devices for the humans and the output devices for the humans. So, controllers are essentially the input devices, the displays are the output devices. So, the controls can be something like a microphone. A microphone is not something that you touch with your hands, but it's still a control device. Displays is not necessarily just the monitor, it can also be an auditory display or some tactile display. So speakers, that's the display. Tactile display, such as like a vibrating phone, that's also display. So by display here, it's not just visual displays. Even though semantically in English, display is basically what it is. If you say to display as a verb is show it visually. So in this context, it's not just visual. Control display compatibility. Know what this concept means. So if I'm using the motion of this ball on the keyboard, basically, if I'm using the motion up and down, and the cursor moves up and down, then there is this compatibility. If I'm holding it like this and I'm moving it left to right, yeah, there is some compatibility here. But if I'm moving it back and forth, the cursor moves up and down. So this is an indication that there is lack of compatibility, at least in one axis. So generally, what can also happen, I can be standing facing you, and the keyboard is basically also rotated the other way, and I'm moving the cursor left and right, and I expect the cursor to move left and right at the same time, but it moves in the opposite direction. So things like that are not necessarily obvious for most of the desktop interfaces, but they might be a problem when you have, let's say, a tabletop interface. When you have an interface on a horizontal surface, and you can have people standing around that display from different orientations. So unless you use touch display, many things like using a mouse on the tabletop might be a problem. People might get confused as to what orientation they are in right now. So control display compatibility is something that sometimes matters. So some of the examples, how the mouse moves and how the screen moves. Things about the elevators when you're scrolling the images. So you move the elevator down and the image goes back. You move the elevator up and the image goes down. So various examples of how this might not be direct mapping. So up motion, response to up motion, and so on. So sometimes people can actually learn how things are. So for example, the automatic transmission shifting lever in cars. You have like the park, you have reverse, you have neutral, you have drive. So if you want to go forward, you move here. So this is basically forward. If you want to move back, you move it here.
And then if you fuck up, you put it on neutral.
And then if you fuck up, you put that.
You guys, please talk in a respectful manner.
I apologize. That was
That's hilarious though.
In the airplanes, you can have a similar problem with the throttle. The throttle can go up and down, and the airplane can go faster and slower. The yaw control, of the airplane. So if you push it forward, the airplane will go down. If you pull it towards yourself, it will go up. So again, this is not exactly compatibility. If you push it forward, it will go down.
It goes down, but
Yes.
actually that kind of makes sense.
It makes sense. Like imagine a horse.
Yeah.
So it does make sense, but like think about it. Sometimes it doesn't really work the way you expect it to work. Another thing, sometimes the throttle is actually the knob that you pull out. So if you push it forward, the engine goes slower. If you pull it outwards, the engine will go faster. That's on a Cessna. So on a Cessna, the control is basically a stick which you pull towards yourself to have more power, and you pull it inward, push it inwards if you want to have less. If you want to have less power. I think this is the way it works. Actually, if you pull it. Sorry, I don't remember. It's been more than a year since I've flown Cessna. I was flying basically like 5 times in Saskatchewan. So my friend is a pilot, and sometimes I was having controls. So anyways, control display compatibilities. Another example, turning the steering wheel of the car versus the motion of the car. So you are standing in place. If you are standing in place and you turn the steering wheel, the car doesn't move. It's only the wheels that are moving. So the wheels are moving, but the car is not rotating yet. So essentially, what this does, it controls the rate of rotation times the speed. So if you have non-zero speed, then the car will start churning at a specific rate. So here you're controlling the rate of rotation. In the airplanes, you're actually controlling the second derivative in this case. So if you want to turn, you turn the yoke, the plane will start basically banking. You turn it to the middle, the plane is still banking and it's turning. If you want to fly straight, you turn it the other way, the plane will go horizontal, and then once it's horizontal, you put it in a neutral position. So you're controlling the rate of changing.
The rate of change of the range.
Yeah. Yeah. Yeah.
Are we expected that like answer the difference between turning a car and turning a
No.
car?
I'm just trying to give you some examples how things work.
Okay, cool. Thank you.
I'm not trying to brag about like knowing how to drive a car or not knowing how to fly a plane. So now dimensions versus degrees of freedom. So these things are sometimes confused. So the number of degrees of freedom. How many degrees of freedom do we have in the real world?
Too many.
Well,
6.
if you consider this an object, how many degrees of freedom does it have in this three-dimensional space?
6, was it?
6. So it has 3 degrees of freedom for position. So this is the positional degrees of freedom, and it has the orientation degrees of freedom. This one, and this one. So it has 6 degrees of freedom. 3 for position and 3 for orientation. What about the same objects on the two-dimensional surface? How many degrees of freedom does it have on the two-dimensional surface?
4.
No, just 3. So 2 position degrees of freedom and 1 orientation.
Oh.
You cannot orient it this way, you cannot orient it this way. So we can only orient it this way. So this is about the degrees of freedom and the dimensions. So in 3 dimensions you have 6 degrees of freedom, in 2 dimensions you generally have 3 degrees of freedom. So this is basically what it is. How many degrees of freedom does mouse have?
According to 2.
3. 2. Only 2. It can only sense the position. It cannot sense the orientation. If you turn the mouse in place, the cursor doesn't change. Like, it only senses the position. Mouse does not sense the orientation. It should have, mouse as an object should have this ability, but it doesn't.
The thing with the double, those experiments that Microsoft did.
On the other hand, if you consider other things in the mouse, so you have buttons. The buttons can be used as modifiers. So that's one thing. The mouse also has the wheel. So if you consider the wheel of the mouse, the wheel can actually give you an additional degree of freedom. So let's say you can move the mouse left, right, up, down. So 1 degree of freedom, another degree of freedom, and you can also turn the wheel. So the wheel can be used as an additional degree of freedom. It doesn't map naturally to what happens in the real world. It doesn't map naturally to, like, there is no control display compatibility essentially. So it does not map to what happens in the world. You might want to have this twisting motion be represented like this rotation. If you had a lock on the mouse, on top of the mouse, instead of this wheel, which goes in the opposite orientation, that would be probably better if you wanted to change the orientation. So the mouse with the wheel essentially has an additional degree of freedom, even though it's not mapped naturally to what happens in real life. So subtle point, but yeah, the mouse can also have an additional degree. Also, some mice have the isometric joystick, or some mice can also allow you to tilt the wheel left and right. So this sort of mouse will also have an additional degree of freedom. It will have 4 degrees of freedom. Some mice, such as the Apple mouse, is it? From what side is the Apple logo hidden?
It doesn't really matter.
Such a question.
It's just wrong parents then.
So it's an Apple mouse, and here you actually have the pressure sensing pad. Well, not pressure sensing, you will have like a capacitive sensing pad. So where you can actually move the finger, and it can allow you to scroll left and right and up and down. So this mouse will essentially have 4 degrees of freedom. So it will have the movement sensing degrees of freedom. It will also have the additional degrees of freedom from the very top surface of the mouse. So you can, for example, use them for scrolling the pages, like you would use the wheel, and you can also move them for use them for moving between like the pages before and the pages after, like back and forward in the pages. So if you want to go back to the previous web page, you can use that. You can use that for moving between the applications as well. So again, like this is an additional. So back to what the humans can do. So this diagram, how the systems are being used with humans. So you have some activity, you have the humans performing this activity, and you also have the context of that activity. So let's say I'm using this computer, so the activity using the computer. So I have the keyboard, and that's the computer. I'm using the computer, like flipping the slides, essentially, flipping the slides on the screen. human. Obviously, I'm a human, I'm a professor. Well, instructor, to be precise. I'm an instructor in computer science. So this is the human showing the slides on that computer. And the context here is the public environment with, let's say, 30 plus people sitting in a large classroom, artificial lighting, reasonably quiet environment, and so on. So, human, what I'm doing, and under what conditions I'm doing. So this is basically something that can be used to describe most of the interactions with computers. So you describe who's using the computer, under what circumstances, and what kind of action is taking place right now. So let's say I could be drawing a picture in paint, but this is not something I would do. The human can also be a student. So the students will have slightly different experiences. They will have maybe less experience using PowerPoint. The context can be me being outside on the stage. So there will be much more noise. The environment will be much larger, and the lighting will be mostly natural. So try to think about that, like what the different contexts could be, what different users could be, and what other things they might be doing, which are quite different from the other ones. So let's say me reading a document is not the same as me showing a presentation. So sound localization. So we talked about the visual interfaces, sound localization, how we can tell where the sounds are coming from. So at least I would expect you to know the first two. So the level differences and the time differences for the signals. So how you can simulate the direction of the sound by using either one or the other. The group delays and spectral, these are like much more advanced, and they're usually weaker as well. So the senses which are not included in the classical senses. So the classical senses are vision, hearing, smell, taste, and touch. So the classical senses, the classical five senses is something that like you learn as kids. But there is also other senses. Kinesthesia and proprioception is one of them. And what other one do they want to include? So being able to sense temperature, being able to sense pain. So let's say if I take a needle and I try to poke my fingers, that's basically the pain sensation, and it's not touch. So sensing the temperature is also like it's not touch. Being able to sense the temperature, being able to sense pressure. Let's say if I'm leaning against the board, this is not touching. Like I'm just resting on the board. You cannot really say that I'm touching. Or if my shoes are tight, you cannot really say that it's a sense of touch. Being able to sense the texture, this is not touching. Like I'm able to like feel that this surface is rough. I'm able to tell that this surface is not glass, it's actually something more similar to, let's say, smooth fluid. So these senses, you can see the description of them. Now, other things, you probably should have no problem with Fitz's law. So how humans perform quick tasks. So if you have pointing direction, then pointing direction can very well be described by the Fitz's law, which was originally a one-dimensional law, but there is a very easy extension of this law to 2 dimensions, not to 3 dimensions. For 2 dimensions, it works fairly well. Extending it to a 3rd dimension is quite problematic right now. So the task that you see on this slide is somewhat similar to the task you did in one of your assignments. There is also the graphs that you built, the movement time versus ID, and the ID. The slope of this line and the intercept of this line is something that you were supposed to compute. So A was the intercept of the line, and B is the slope of this line. So the definitions of the throughput, something we probably looked at as well. So this is essentially the 3rd assignment that you did in this course. So you might have some questions about the Fitts law, about the throughput, about why we have the throughput, and so on. Also, the next topic is evaluation. So we covered evaluation sort of twice from different in different contexts. One of them was evaluation per se, another one was the usability methods. So the usability methods are basically the methods which are used during the design of your system. So you might use some of the usability methods which are not evaluation methods. So some of the methods would be like picking the best layout or something like that. So it's not really evaluating it, it's more like designing something. So evaluation methods. Analytic, expert evaluation. Expert evaluation also has a subtype called heuristic evaluation. Heuristic evaluation is the expert evaluation which uses a specific set of rules. So you come up with some rules, let's say like 9 or 10 rules that are described by either Jacob Nielsen or Van Schneiderman. You use the rules, and then you will basically have the expert evaluation, which is called heuristic evaluation, because you use the heuristic rules. Then observational, you can use like video cameras, you can observe people, you can do surveys, and you can also measure something in a scientific manner. You can have users perform some performance-based tasks. You measure their accuracy, you measure their speed, then you apply the scientific method, you evaluate the results statistically, you present them, whether the difference was statistically significant or not. So that's yet another kind of evaluation. So this is the scientific, this traditional scientific evaluation of things. The same way people would, like the scientists would evaluate the efficacy of drugs, the epidemiological influence of different environmental factors, and things like that. So here, you're basically applying some statistical analysis at the end. For the other ones, it's mostly qualitative in many respects. So expert evaluation, the rule, is the principle violated or not? So this is more qualitative. Analytic evaluation, you're computing some numbers. So selecting a button takes, let's say, 300 milliseconds. You have 4 buttons that you need to select. 4 buttons times 300 milliseconds is going to take 1.2 seconds, and so on. So analytic evaluation, you crunch the numbers, essentially nothing else. Observational, you take a video, you analyze the video. For example, you say, okay, like this is how many times students or users made an error in using this user interface. And surveys, you're just gathering the information about whether it's feasible to tackle this problem or not, or how many times users found the problem, the software to be problematic to use, what wishes they have, that sort of stuff. So experimental evaluation, system A was let's say 20% faster than system B, and this is within like the confidence of this conclusion is like 95%. So experimental design. Things about participants, like the information that you gather from the participants. Most of this is fairly obvious. It's mostly the demographical information. So things to mention is, do not call your participants subjects. You can call them users. If it's HCI, you can call them users, but calling them subjects is something that is dehumanizing, basically. So subjects is something that you might apply to animal testing. Yeah, so like if you use guinea pigs, maybe you can say the guinea pig was subjected to the following treatment. But subject is not really something that sounds good for the human participants. So independent and dependent variables. So the variables that you are manipulating are the variables that are called independent. So independent means that you are changing them at your will. So it's the variables that are changed on their own. Like you want them to be changed and they have their own will and they change. So they're independent, nothing can prevent them from changing. So you manipulate them in your own experiment. So this is why like you change them without, like the variables are not influenced by anything else, it's only influenced by the experimental design. So the experimental design says these variables should take the following 10 distinct values. And once they are set to the 10 distinct values, then you measure the dependent variables. The variables that depend on the independent ones. So in your experiments, let's say you were using the, well in this case there is no example, the independent variables in the fifth law experiment was the target distances, the target sizes, and possibly the number of targets. But the most important ones are the target distances and the target sizes. So measurement, you were measuring the movement time. Movement time was the primary one. The software would probably give you the percentage of errors. So percentage of errors, again, that was the dependent variable. So let's say the speed depended on the target sizes and the target differences. The error rate might have dependent on the target sizes. So if the targets become smaller, the error rate goes up. So these are basically the performance measurements that you would collect. So in assignment 3, you use amplitude and width as independent variables, and you use movement time and error rate, for example, as dependent variables. You have to report only the movement time source, maybe the throughput as well. I forgot what. So the other kind of variables that you might hear sometimes about is the control variables. So the control variables are neither. So the control variables are the variables which you want to keep constant. So let's say if you're doing an experiment, the values that you want to control is the amount of light. So let's say if you use artificial lighting, then it's better to just like close the blinds or something like that, so that the amount of light does not depend on like whether it's sunny outside or not. So that's one control variable. Another control variable, whether the users are, let's say, left-handed or right-handed. So let's say if you're testing a keyboard and one of the people is right-handed and the other people are left-handed. So if you want to test the keyboard, and obviously keyboard is non-symmetric, then you might want to control that. Sometimes you might want to actually not control that. So if, let's say, 10% of the people are left-handed, you want to have the external validity so that the general population using this keyboard will behave just like your sample of users, which contains 10 right-handed people and 1 left-handed person. So another kind of control variables would be temperature in the room. Let's say people might be shivering when it's like only plus 12 in the environment. So if you want to test text entry outside right now, you might have different performance just because people are uncomfortable being outside when it's winter. So that's the control variables. I don't think I've mentioned them in this set of slides, but I'm just letting you know that they exist, and they were mentioned pretty much indirectly. You do not report them usually. You just say, okay, like the environment was the following, and we tried to keep these conditions stable. So that's the control variables. For the final exam, I suggest you learn what the independent variables are and what dependent variables. Then user-centered design. So in case I decide to ask what user-centered design is, know the definition and try to understand what is behind that definition. The steps of user-centered design. So this is something that we can also group. So this is the actual design. This is the testing, and this is like collecting the information before you start the design. So you can basically group them into 3 groups. You have that in your slides as well. This table, which summarizes all the different usability methods. So note the sum of them are the methods of doing evaluation, and the other ones are not about evaluation. They are mostly about just like analysis about like the stakeholder meetings and things like that, brainstorming sessions. So some of them are not evaluation methods. Some of them are only used for the design stage in order to make the design better. So they are usability methods, but they're not evaluation methods. Let's say brainstorming session. This is the session where you gather supposedly intelligent people who will come up with multiple versions of the same design, and you will try to get the best ideas from each of the proposals. So this is what the brainstorming session is. You solicit multiple people for ideas, and then you record all those ideas, and eventually you might want to combine them in order to like have the best possible design. So look at this table. Try to recall whether we covered anything in class, like what it was, like how you would use, let's say, Wizard of Oz. What is Wizard of Oz other than the movie? So try to think about what these methods are, and try to be able to explain the significance of all of these methods with your own words. Do not try to just memorize everything. Like most of these methods actually make sense. It's not something that, okay, like this is like the best of the best user evaluation method, the best user experience method which we had like in the last century. So here is the paper that we published. We did the following research in order to come up with the Wizard of Oz. Wizard of Oz is something that people did many times before. Like they had those supposedly machines that were playing chess. That was Wizard of Oz. Do you remember that Mechanical Turk system? So Mechanical Turk was essentially a cabinet similar to this. Cabinet maybe not as tall. There was a person inside the cabinet. A person who could play chess really well. And he also had like a doll, well, not a doll, like the human-like figure, which would be sitting behind this cabinet, and that figure could move the artificial limbs in order to move the chess figures. So people will pay money in order to play with the machine. So they thought that they were playing with the machine, but the actual thing that they were playing against was actually the human who was inside the machine. So the human inside the machine was controlling the artificial arm of that player, and the player was moving the figures, and whoever was playing against that supposedly machine was convinced that they were playing against the machine, even though it was actually a human player. So that's the Wizard of Oz technique. It has existed for a long time. It's sort of like to fake the experience of the users. So the users were thinking that they were interacting with the machine, and they were treating the device they were using as a machine. So because if you know that you are working with a human, then you treat humans differently from the way you treat machines. Like for example, if I were like if I'm typing the text on these slides with this keyboard, I can like basically slam this keyboard lightly into the board. If I had a human writing things for me, I will not slam the human into the blackboard. So the way you treat humans and the way you treat machines is different from the psychological perspective. That's why you use the Wizard of Oz. It's an ancient technique. Parallel design. You design multiple things at the same time, and then you see if like which design is better, what are the best features of each of the individual designs, and so on. Storyboarding, you just like put all of the commands, all of the actions of people into the storyboard, like where you like record what they do, when they do it, what they think when they are doing it, and this is how we can visualize how people will use your system. Card sorting. So let's say you have multiple features, and you have, let's say, 25 features, and some of them are easy to implement, some of them are more difficult to implement, and some of them are more important, other ones are less important. So you put them all in, on the cards, like on small index cards, and then you give the potential users, for example, the stack of cards, and let them sort all of those features in terms of importance, in terms of their grouping, let's say what features belong together, that sort of stuff. So this is card sorting. I'm pretty sure that card sorting is not something that is used only in human-computer interaction. It's not something that is used only in design even. So like people might use card sorting to design electronic things without like any interfaces whatsoever. You might design, okay, this is the feature we want to have, this is the feature which is not as important. Let's say you have the automatic transmission of the car, and the example of such features would be whether you use the wood material or whether you use the aluminum material as a surface for the surface of that shifter. Or whether you want to use alloy wheels or whether you want to use steel rims for your car. So that's card sorting. Focus groups. When you want to get some opinion from the general public about your design. So that's the focus groups. So look at all of these, try to recall what each of those mean, and try to like be able to recall them during the time. So latency, dropouts, latency jitter, tremor, and so on. So know the definition of what latency is. Latency is not like people coming late for class. Latency is something that is somewhat different. So like that's the delay in system's response. So you tell the system to do something, let's say move the cursor, and the cursor doesn't move for another like 200 milliseconds. So that's latency in the system's response. What they come from, this is like a small subset of like where the latency can come from. Sample rate. Let's say the camera is not taking frames often enough. So if the camera is working only at 30 Hertz, so 30 frames per second, then each image takes like about 33 milliseconds to be taken. So that's the frame rate. Noise processing, if you have to like buffer multiple samples and you have to average them. So until you receive enough samples in order to apply the filtering, you have to like wait. Physics limitations, one of them could be how fast you can move your limbs. So let's say the maximum speed you can move your limbs, like that's the force that your shoulder muscles might have, and also the mass of your arm, mass, not weight, the mass of your arm, so this is inertia. Signal propagation, if you use acoustic sensors, signal propagation might be of an issue. If you use long distance networks, signal propagation again might be an issue. So let's say you're playing network games with someone on a different continent. So signal propagation might become important. Latency and jitter, fluctuations of latency, like at least know what it is. Dropouts, try to know what it is, like where they come from. They can come from UDP packets, which are sometimes dropped. They can also come from unreliable links, such as wireless links, or someone turning on the mic page. Spatial jitter, so it's the jitter, but not in time domain, but in space domain. So jitter, which is essentially the shape of the cursor. So if you take the position of the position that the sensor records, sometimes it will not be the same. So the sensor doesn't move, but the position that the sensor records are fluctuating. So this is the spatial jitter. How you can use one to compensate for the other. So how you can buffer several samples, you can, let's say, average 9 samples or 10 samples at a time. So you take 10 samples, you compute the average. This way the fluctuations will be decreased. So let's say this line will become smoother. But since you're averaging 10 samples at a time, the time that these 10 samples take will be adding to the delay. So whatever happened 10 samples before will only have the effect now. So by averaging the samples, you're introducing more delay. So there is a disadvantage there. You're making the motion smoother, but so the advantage here, you're making the motion smoother if you do the averaging. But the disadvantage, the price you have to pay, will be you will introduce the delays in the system. So the cursor will move smoother, but it will be slower. Slower in the sense like it will not respond as quickly. So there was an example here. Why we have this 3 square? This is basically how the noise is reduced. In order to reduce the noise by, let's say, by a factor of 9, you have to use, in order to reduce the noise by a factor of 3, you have to use 3 to the power of 3 squared number of samples. So essentially, averaging n samples. I forgot what how the formula is written usually. I think it's about variability. So instead, when they have n samples, let's say the number is the numbers can be from the range 1 to n. Then okay, I'll try not to do it here. So for reducing the noise, I just do not want to write a formula which might be from a different domain. So anyways, if you want to reduce the noise, you average the samples and you reduce the noise by the square of the number of the square root of the number of measurements. So if you average 10 samples, it will be the square root of 10 factor in reducing the noise. So this is why you average 9 samples and you reduce jitter by a factor of 3. If you average 16 samples, you will reduce it by a factor of 4. So that was just an example of that, and I think it's pretty much it. One of the things that I did post on the web page was those side notes that we had during class.
Notes that is on a sample slide with some.
Yeah. So many of them were not in the slides themselves. Is it going to open or not? This is actually a usability flaw of the typical computers. So the time it takes for your tablet to start is typically less than a second. You push the power button and then the tablet is pretty much immediately usable. For this computer, it takes like 2 minutes. 2 minutes to just put into the operating system.
So, but the tablet takes a long time to put.
But you don't have to. You don't have to shut them down. If you put them into standby, they might consume like no power whatsoever. If you put these into standby, they will still consume like 5 watts. Okay, so I think most of you noticed that I posted some of the information about the projects and the fact that the assignment is optional and so on. So the typical format
That is not clear is what time of tomorrow is submitted? Is it?
I think you can try to assume by the last minute of tomorrow.
Okay, cool. So it's only 3:59 is cool?
Yeah, if you're in a different time zone, let's say if you're in Vancouver, you can submit it by 3 a.m. the next day.
Okay, yeah, let's move to Vancouver.
Yeah, feel free to do that. So that's the typical format of like what I expect for submission of the project. In some cases, we had this discussion with several groups. In some cases, it might make no sense doing this a specific part of the submission. So anyways, what you're submitting will depend on what you do. Okay, Okay. Regarding assignment 5, you probably know by now that if you do not submit it, then the previous 4 assignments will be scaled in order to adapt to 30%. If you do submit it, it will only be counted if it increases your grade. So if your grade doesn't go up if you submit assignment 5, then only the 4 assignments will be taken. If it improves your grade, then assignment 5 will be calculated into your final. So that's about assignments.
What is prototype 1 and 2?
So in project 1, part 1, you said?
Yeah, it has 2 prototypes. The first one is the one we already submitted.
Yeah, so you might have multiple prototypes. You might have, let's say, 5 different prototypes you were improving on. So let's say one could be like a paper prototype. There could be maybe like 2 paper prototypes that you like refine over the course of your evaluation. Then you might have one prototype that you tested. It's something that, let's say, you wrote in Java. You did some usability testing, and once you do the usability testing, you discover, okay, here is the flaws that we have discovered. Let's just like redesign the slide. So you will have potentially more than 2 prototypes. And here, like by prototype in the final submission, I mean the final prototype. What you do with the previous ones, you will document them in your report. So let's say before we arrive at the final prototype, at the final submitted system, we had the following iterations. So we started with the paper prototype, then we did some meetings. During the meetings, we refined the paper prototype to the following design. Then the following design of the second paper prototype was implemented in Java, and then we noticed the following flaws. It didn't work quickly enough, it crashed a few times, then we debugged it, we changed the design to the following, so that's why we had like 2 paper prototypes, we had 2 Java prototypes, and the final design is the result of the previous ones. You can also say why you have
Do we have to have 2 prototypes?
that was an example.
I have a question.
Yeah.
So what do you expect from the presentation?
From the presentation, try to convince me like in 5 minutes that what you did actually works and it works well. So that could be a short video, let's say video of like 2 to 5 minutes, where you record the user using the system. Like try to sell me the product that you developed. Like try to convince me that what you did was actually worth doing.
So like a manual or instruction?
Not the manual, it's like the presentation of your software. Like, look at how Microsoft presents the newest versions of Microsoft Office. Look at like how people present their applications on like iTunes or Google Play. Like here's the application which allows you to like launch birds and pigs.
Let's use some tongue in cheek people in there.
So so what I posted here, the examples of potentially poor UI, that was something that we covered last class. You can use them for inspiration, and maybe you will find them useful for answering the questions on the final exam indirectly. So they are not directly applicable, but they might add to your inspiration. These are the side notes, which again, like they're not directly applicable, but it's sort of things that happen in the actual designs, like the problems with large screens, the problems with the hardware design. What is this for you?
Did you see the gun?
Gun using no. So other things, problems with the ICAL, and I think that was the last issue. So I'm not saying that they are something that you will be studying for final exam, but if you might find them something. Did you have a question?
Oh, yeah, for the report, the evaluation, can can we just choose like a heuristic evaluation, or? Just
Yeah, so, did I mention it? Like basically you can have, at least like 6 different ways to evaluate the interface. Some of them are directly applicable, some of them do not apply at all. So let's say if you develop your system, which is one of a kind system, you cannot evaluate it against any other system. So if you look at this graph, so test and measure ones. So diagnostic evaluation is basically making sure that your system just works and doesn't crash, it doesn't have any fatal flaws. So that's diagnostic evaluation. Performance testing, you might say, okay, like the following actions will take this much time to perform. Let's say opening a document will take, like starting an application and opening the first document will take 5 seconds. Subjective evaluation, you can have multiple subjective measures that you might ask people to evaluate on. Let's say the software was aesthetically pleasing or not. The software was causing my eyes to be tired or not. The software was like slow or it wasn't slow and so on. So it's subjective evaluation. Critical instance technique that's slightly more advanced, but basically this is what went wrong. And this is why it went wrong. Like partially it's because the user made an error, but partially it's also the system's fault because the system could not recover from that error. You can also try to measure pleasure. Like there are different questionnaires like were you happy when you were using the system? Would you use the system again? Like would you use it like on Sunday morning? Things like that.
Would you use it on a Sunday morning or on a very cloudy Thursday?
Yeah. So even though not all of these metrics will apply, like look at the 5 evaluation methods at the beginning of the course. So where you had the analytical evaluation, the expert evaluation, the questionnaires, and experimental evaluation and so on. Some of them might apply to your design, and some of them are for something completely different from yours. So you can take this column, and in addition to that, you can take some of the 5 evaluation methods that we had at the beginning.